So what we're going to talk today about is hardware-software co-optimization for machine learning at the edge. I'm Giovanni Ansaloni, and I work in beautiful Lausanne in Switzerland. There's already a lot of content for a single slide, so let me go step by step in there. EPFL. EPFL is a little polytechnical school in Switzerland. There are two polytechnical schools, ours and the little one in Zurich. Founded in 1979, 11,000 students, quite a lot of PhD students. It has 5 schools, and I wrote that down because it's like the 7 dwarfs, so you always miss one. These are architecture, computer science, basic science, engineering, and life science. Myself, I work into the engineering and especially the electronic engineering school. It has 20 institutes and is structured in laboratories. There are 371 of them. Last time I counted. I don't know all of them. I just know that they exist. And in particular, I do work into the embedded system laboratory. It's a rather big one. We are around 40 people, many interns, many PhD students coming and going, so the total may vary. But we are organized with 1 professor, 1 senior researcher, that's myself, a number of postdocs, engineers supporting us, and quite a lot of PhD students and interns. There are no photos of all of us together. This is the closest approximation I could find. And you can see myself here in the white circle, and as usual, my son is still in the scene and making the best smile of the entire photo. What we do is research in an area which spans everything from circuits up until algorithms related to smart devices which have to perform complex functionalities within really constrained computational and energy envelopes. We aim to apply that to very concrete scenarios, going from thermal modeling to smart cells to different types of domain-specific accelerators. And in my 4 lectures, so it's only 4, not 5 in my case, I will try to give as many examples as I can possibly get on how we do that in very practical cases. About myself. So I'm Italian. I've been around in Switzerland for quite a lot. I did my PhD in the Italian part of Switzerland, and then I went back and forth in between the French part and the Italian part 4 times. And as part of my PhD, and since then, what I did was to research the hardware-software co-design receipt. The way I decline that is that on one side, I take a hard look at application domain and see what are the actionable opportunities and challenges which are present not in a single application, but in an entire domain of application. Are there computational patterns which we can exploit? Is the application robust to perturbations, and so on and so forth? Then I just turn around and I interface with people working at the technology level, and I ask them what they have to offer in terms of technology advancements such as no volatile memories, analog computing, and so on. Then I merge what the technology has to offer and challenges opportunities at the application level in order to build computing architectures and software optimizations which can abide to the application characteristics and minimize the energy consumption. Not unsurprisingly, then, what I will cover during these talks are different strategies which either myself or some of my closest collaborators have devised in order to achieve this goal. Today, we will talk mainly about algorithmic optimization, so the what. In the other lectures, I will instead turn page and I will talk about how to compute. We will start by looking at component level optimization, and then we will transition towards more system level aspects. So this is about me. What about you? How many of you are in the embedded architectures? Let's do a raise of hands. Okay, quite a few of you. And what about Edge AI? Also algorithmic people. Anybody in system simulation? Good. So we have representatives from all three of these topics, and I will delve into that in the next 5 hours. So any other topics of interest that you would like to mention? Raise your hand in case. Okay, not today. But hopefully there will be enough ideas for you to build on those topics in my cycle of lectures. So why are we here? The main motivation, and you have seen this slide in many different ways from many other speakers, is the explosion of artificial intelligence. Actually, I would argue that there are multiple explosions of AI happening. From an application perspective, this was 12 years ago, and we were amazed how we could classify cats and dogs, basically. But this is the state of the art here. Using transformers, we can generate videos starting from text prompts. And the fact that there are only 12 years in between this side and that other side is something which I find truly amazing. And I have to revise this slide basically every time I give this talk because the progression is so fast. There is another type of explosion, and it is the explosion in the hype related to artificial intelligence. This can be declined in 2 different ways. Either we are doomed because of artificial intelligence, or artificial intelligence will solve all of our problems. Actually, my favorite one is the one of the New Yorker, which advocates that, yeah, AI is good at doing tasks, is not that good at understanding which tasks it should actually be doing. So in this case, the task should not be piling crumbles of paper, but actually producing a nice text. Nonetheless, tasks it does, and the reason, or one of the main reasons why it's able to do more and more complex tasks is the second explosion of AI, which is the explosion in AI size. I'm not saying here that algorithmic updates are not important. What I'm saying is that quantity has a quality of its own, and we can see that whatever metrics we take, we may take number of parameters, number of operations, the only way is up, basically. So what about the edge? Well, we would really like to have AI at the edge because it gives us fantastic opportunity to develop latency critical applications. So we don't have to transmit data around to give the user some response, or in scenarios such as healthcare in which we have privacy concerns, in scenarios in which we want extreme energy efficiency. Don't forget that data movement, especially across a wireless link, is expensive. So if we can avoid that and do everything locally on an edge device, then we can have an increase in energy efficiency. And then there are opportunities which are specific to the edge scenario, such as personalization. If we want to give smart devices to people, everyone is different. So we would also like to personalize the type of computation which we do to every person which uses a device. This could enable potentially many different scenarios which we call edge AI. Just a disclaimer, the type of edge really depends on the scenarios which we have. So the computational capability which we can have into energy harvesters are very very different with respect to the ones which we have in augmented reality, in which we can perform quite a lot more computations. Nonetheless, in all these scenarios, from deep, ultra-low power energy harvesters up until more capable devices. AGI is summarized in a tension between AI, with these millions of parameters and billions of multiply accumulate, and the edge part, which can be battery or vessel powered and have a small energy and computational envelopes. So our goal here is to bridge this gap. Without further ado, let's go into the what to compute. But before that, we have to address that the computation can be done in different ways. The simplest type of computation which we can do is basically just signal compression. We just take the signal as it is, we compress it in a low power way, and we rely on something else to do something smart. Or we may have a features-based flow in which we extract something which we know is significant, and we know it because, for example, we have spoken with an expert in the particular field of that application targets. And the third level is one in which we try to do the interpretation of the data locally using deep neural networks. In all cases, we need data to do that. And this is a problem of its own, because each scenario may have different metrics, different figure of merits, different data sources, and this greatly impacts reproducibility. If we have these 3 papers, we may say, oh, this is 99%, is the best one. Well, maybe so, maybe not. Because if we delve a little bit deeper, we see that in all 3 cases, the data sets which we address is different. The type of task which we do can be different. In this case, we have a teacher-student type of scenario in which we have a generalized model and a personalized model. And also the performance metric may be different. So comparing things can be tricky. Different data set, different machine learning task, different performance metric, and so on and so forth. So what is needed is our data sets and ways of annotating the type of events which we want and the type of scenarios which we address in a standardized way. For image recognition, we have ImageNet, which is a very nice starting point, but in many edge cases, for example, in the healthcare domain, we don't have the same type of standardization. My good friend and colleague Jonathan Dunn, which is also working in my research group, is tackling this challenge by introducing SzCore. What is SzCore? It's a framework for the validation of epilepsy detection algorithms using EEG, electroencephalogram. What it standardizes are the type of signals, the type of annotation, when a seizure starts, when it ends, how much it lasts, and the way the data set itself is organized. More than that, it also provides metadata which allows to define what is the type of metric which is used and what is the type of scenario. Are we doing a teacher-student type of thing? Are we doing a personalized algorithm type of scenario? And so on and so forth. So this is very much a first step because it's very much specialized towards seizure detection, but his goal is to extend that to multiple edge scenarios. It's very much a work in progress, so if you want to know more, just take a look at his GitHub repository. The QR code is present here. Now, let's say that we have the data. So what can we do with that? The kind of ground zero for having an edge AI device is just to compress the data, either to store it or to send it to somewhere else. And this compression can take advantage of how the data is. So if we have a biosignal, in this case I'm showing you an electrocardiogram, then it may be sparse in a given domain, or it may be self-similar. In the following slide, I will show how these characteristics can be leveraged in order to do something smart. So if a signal is sparse in a domain, it means that it can be represented with few coefficients, at least in an approximate way. In the example of the ECG electrocardiogram, we have that the sparsity is pretty high in the wavelet domain. Up until here, we have coefficients which are significantly different from 0. Afterwards, not so much. So, what can we do with that? We can transition to the next slide, for example. We can apply a technique called compressed sensing, which is very computational efficient on the compression side. What it does is that it takes a window signal, multiplies that with a measurement matrix, which is rectangular, so it compresses the input signal, and is only composed by zeros and ones. So basically, you add up some of the elements of the window, and you have a number of linear combination of your input samples. This is a very energy efficient way of compressing your film. The downside is that the reconstruction becomes more complicated because it involves solving a convex optimization problem in which we're trying to recover what are the wavelength coefficients subject to sparsity and to an error constraint. I put this formula for the more mathematical inclined. I'm not going into the details of that. Just, this is complicated, this is simple, this is complicated. How well does it work? Well, it really depends on how sparse your signal is in the target domain. ECG, wavelet domain, sparsity is pretty good, so the coefficient decay pretty fast. So we can have a 50% compression ratio, so we can shrink our data by half while having still a very good level of reconstruction. These good and very good level are kind of defined in literature in terms of PRD error. For other type of signal, your mileage may vary. So for EEG, it still kind of works. If you're looking at electromyograms, which is the measure of the signal given by muscle contraction, then they are not very much sparse in the DWT domain, so compressed sensing may not work. And this is kind of a common pattern. You have to look at what your data is, and depending on that, then you will have a proper strategy in order to address these characteristics. This is why it's hardware software co-design. Can we do better? Yes, we can. So usually we don't acquire a single ECG signal, but we acquire multiple ones. This is a 15-lead ECG signal, which, if you want, is kind of an overkill, especially for a wearable device, but is to give you an understanding of how things may go. And by using the same strategy for the sensing, so still using a random matrix only containing zeros and one, and complicating a little bit how we do the reconstruction, so we not only look at the coefficients in one signal, but we also look at the correlation across signals, then we can even compress further. How much further? Well, this would be the normal reconstruction, and this is the reconstruction using mutual information along the different ECG signals, or more properly ECG leads. So signals are acquired from different contacts. Oh, sorry. What we can achieve is, instead of having a 50% compression ratio, now we have a 72.7 compression ratio, still for a very good reconstruction, which is not bad, taking into account that we only took some random samples and we added them together a bunch of time using the matrix with zeros and ones. Second characteristic that a signal may have, so we have seen sparsity in a domain. Now let's look at similarity. So if we look at ECGs, every orbit is kind of similar to every other orbit. So what we can do is that we take templates of one orbit and then few samples of all the other orbits, and we try to use the templates in order to reconstruct the missing part due to the sparse acquisition. This is particularly interesting if we are using an event-based sampling. So what is event-based sampling? It's a very fancy way of saying something which is pretty simple. In time-based sampling or uniform sampling, every so many milliseconds you acquire a sample. In event-based sampling, if your signal crosses a given threshold, then you acquire a sample. So you have samples which are always at the same levels, but at non-uniform moments in time. Once we have these samples, which are at non-uniform moments in time, then we have to interpolate them. How we can interpolate them? We can use linear interpolation, polynomial interpolation, sample and hold, splines, or, as I was mentioning before, we can use similarity. How to do similarity? Well, we can have to take a template and then deform it so that it passes through the samples which we have acquired. What does it mean to deform it? It means to shift it up and down and to stretch it left and right in time. This is a very well-known technique in signal processing, which is called dynamic time warping, which is used to put together two series. The main idea behind dynamic time warping is that you start at a sample and then you decide if you want to take the next sample in the source sequence and the next sample in the target sequence, or you want to take the same sample in the source sequence and the next in the target sequence, on the other way around. So if you have the source sequence and the target sequence, what you have is a path in a matrix in which you have all the samples of one sequence and all the samples of the other. In our case, it's a little bit more complicated because the two sequences which we have, the one of the template and the one we have just acquired, have a different length because one is compressed, and also the one which we acquire using events-based sampling has a varying distance in time in between the different samples. So the math becomes a little bit more convoluted. It uses the first derivative instead of the values, and it uses a notion on time in between the different samples. The fact that I put that in a square like this means it's a little bit more complicated. All the details are in the paper. I will not explain it here, okay? The last problem which we have is that we have to select the templates. So what we have to do in this case is to acquire a number of orbits and then do some clustering. The centroid of each cluster corresponds to a template which may happen quite often in our sequence, so it's an interesting one. We take the arbit which is close to each centroid as a template. This is the whole methodology in a snapshot. So we start by taking few arbits, and then we divide the different arbits, and then from there we say, okay, are we happy with our template set? Yes or no? We are not happy. We take more templates. Fine. Now we are ready to do our event-based acquisition, and each time we acquire some samples in an event-based way. We just stretch them according to the templates we have, and we do the reconstruction. Our template set is no more very good. We start an acquisition of another template set. Does it work? So this is kind of the midpoint in the arbits which we had. We had 50% worse reconstruction than this, 50% better reconstruction than this. The blue line is the original arbit. The green line is what we would have with the linear interpolation of our events as they are acquired, and the orange line is the one in which we applied our methodology of stretching templates. And you can see that, yeah, it's kind of better than just doing linear interpolation. These are aggregate results which we got of a very big database. Yes, it is better. When I put a reference in red here, it means that this is the paper that I'm talking about. All the details are there if you're interested. Can we do other things with event-based sampling? Well, maybe we are not really interested into reconstructing our acquisitions, but we would like to do something else. For example, detecting peaks. This is very common when we're doing biosignal analysis. In EEG, we have spike detection. In ECG, we are interested into detecting the RR rate or the different characteristic ways of an arbit. So detecting peaks is kind of important in many edge scenarios. In an event-based kind of setting, this is very simple. If we have a sequence of upward crossing and then a sequence of downward crossings, then in the middle, we will have a peak. Can we do smoothing? Yes, we just aggregate the up crossing and the down crossing in a window, and our signal is automatically smoothed in the event domain without needing any type of reconstruction in the time domain. Can we detect seizures? Yes. Usually seizures are characterized by quite violent changes in the EEG signal. So by measuring how long is the line of the signal in a window, we may have an idea if a seizure is occurring or not. And so on and so forth. So one question which we do have is, generally speaking, if we have an application in which we are interpreting a signal, should we do that in a time-based way, or should we do that in an event-based way? This is very much work in progress, and this is the reason why this figure is so complicated, because we haven't found a way to simplify it further. But let me try to go through that in a second. So we have three scenarios. One is the standard ADC. We take a sample every so many milliseconds. One is a subsampler in which we start with the standard ADC, but we decimate the signal, only taking the samples which crosses different levels. And the third one is a complete analog solution in which we have an event-based ADC to start with. The application is HiPEAC detection, and here we're varying the data race, so how much data we're starting with, and on this axis, how much of this data is useful for the particular application. In this regime, we have high data rate and low noise. Here you have low data rate, low noise. What I mean by that is that if we increase the noise, then we will have more data in an event-based scenarios because we will have more crossing of levels. But quite a lot of that will not be very useful because we are only interested into detecting this peak. Here the data is very clean, and we have that the informative data is quite a lot with respect to the data which we are acquiring. So what we have observed is that if the signal is very clean and we are sampling it very fast, then we should go for an event-based ADC. But maybe this is the least interesting scenario, because if you have a lot of data, the signal is very clean, then basically everything works. A little bit more interestingly, if our signal is very noisy, then we would like to start sequencing our signal with the standard ADC and then decimate that using events in order to drop samples before an analysis. As I mentioned, this is very much initial work, so if we meet again next year, I hope to have much more results about this event-based versus time-based comparison. What I did in the last couple of slides was transitioning from a compression of the signal to an interpretation of the signal. So under the hood, now we're talking about feature extraction and classification, and no more about signal compression by itself. Why we would like to do that on Node? So this is a little experiment which we did with a rather standard setup based on an edge device which was called the Shimmer. And on one side, we were acquiring and transmitting an electrocardiogram signal. On the other side, we were acquiring, doing some processing to discern the start, the peak, at the end of the three characteristic ways of each heartbeat, and then transmitting that. We can see that even if we were using Bluetooth Low Energy for transmission, which is pretty energy efficient, just transmitting features in practical scenarios is way better energy-wise than just transmitting the whole sequence. And this is not only kind of a toy example, but this fiducial point of heartbeats have a great medical relevance for cardiologists. So it's something which is actually practical, useful in the medical domain. And this points out to a more generic flow, which I call in this slide a features-based flow, in which we do some conditioning of the signals to remove different sources of noise. Then we may fuse the data which we acquired with multiple sources. For example, if we have an EEG cap, we may have 10 or 20 electrodes. If we have ECGs, we may have 3 or 6 electrodes. We do some feature extraction, and finally, we may do some classification of relevant events. Pros and cons of this flow. So we can easily leverage expert knowledge because we can ask experts in the application domain, for example, medical experts, what are the features that they are interested into, and code some signal processing routines in order to extract those features. It allows for low-level optimization because, by and large, we know what we're doing. And this will be clarified a little bit in something like 15 minutes from now. On the other hand, it poorly generalizes. So we are doing some applications and writing some code which targets one specific application, and we want to do something different. We basically have to start from scratch. The fact that I'm presenting a flow, giving it a name, discussing pros and cons, kind of foreshadows that there will be another flow which I'm going to talk about in the near future. This is a practical example of how this can be embodied. So let's say that we are acquiring 3 ECG signals from different locations on the body, and we want to know for each heartbeat the start, the peak, at the end of all the waves. What we have to do is to filter the signal, combine them, and then do some delineation. Filtering. So there are 2 sources of noise which typically corrupts an ECG signal. One is baseline wandering, so the signal slowly goes up and down. Another are high-frequency noise. Morphological filtering uses sliding windows in order to get rid of baseline wandering by using very large sliding windows, and also high-frequency noise by using very small windows. Spline filtering just takes a knot in parts of the signal which don't have any electrical activity coming from the heart and estimates what is the wandering which we do have. Data fusion, well, there are many fancy techniques to do that. In this particular example, we just went for something which is very simple, which is sample-wise root-mean square combination. We take every sample in the sequence originating from the different leads, and we just compute the RMS combination, which is that formula there. Delineation is basically where the magic happens. And in this study, we again use 2 different techniques. The first technique is intuition from the fact that different waves in electrocardiogram have different frequency content. The first and the last wave are called P and T waves. They have a much lower frequency than the QRS complex, which is the biggest peak which we have in the middle. So, by using a series of field filters, we can highlight the different waves and discern where we have the onset, the peak, at the end of the different waves. Alternative, we can use, again, sliding elements which do moving averages. This is called morphological delineation. This is the time-based signal. This is the signal after morphological delineation. And we can see that we can detect the peaks as valleys and onsets as peaks. It's pretty straightforward formulation in which we just take what is called a structuring element, we slide it through the signal, and we take the maximum onto that sliding window. Does it work? Yes, it does. And the takeaway message of all that is that by doing this kind of specialized processing, you can reach quite high performance. And here I'm showing the start of the first wave and the end of the last wave, because these are the most challenging fiducial points. The others are way easier than that. And we can get good performance while using very few resources. So this thing produces something which is relevant from a cardiologist perspective while running on a device which has a grand total of 96 kilobytes of RAM. These are not megabytes, these are kilobytes. and it works at a whopping 6 megahertz. So you can almost make mechanical devices which go that fast. Now, can we do better if we are targeting a specific application? The answer is yes, if we are picky in the type of data which we want to provide to the end user, for example, a medical doctor. So not all orbits are born the same. There are normal orbits, which are kind of boring, and there are abnormal orbits, which originates from pathologies or different type of events, and these are more interesting from a medical perspective. So we can just have kind of a preprocessing which only takes one input, does the RPEAC detection, which is the detection of the biggest peak of an orbit, and says, okay, so this is normal, this is abnormal, and only for the most interesting ones, which are the abnormal orbits, then we do a more detailed delineation of the fiducial points. By doing that, we can have quite a lot of reduction in the runtime, 60%, and we can catch 90% of the abnormal orbits. This is a little bit more general than this specific application, because it points to an incremental classification strategy in which we spend more and more effort. Either the more interested we are in the data in which is being acquired, or the more unsure we are about the meaning of the data which is being acquired. So I actually, together with my colleagues, investigate this last scenario in the past few years, and I will show you a couple of methodologies which try to address it. Such scenarios start with the extraction of few features, and then the detection of something, and I will go into more details about what this something may be, and then a measure of trust. Do I trust the results? Yes or no? Okay, I trust the result, okay, I'm done, and I can just sleep up until the next window of signal is ready. I don't trust the result, I compute additional features, and hopefully now, with these additional features, I can have a better idea of what's going on. And I go round and round until either I arrive in a situation in which I do trust the results, or I just give up and finish my feature sets. This is multifaceted, this type of challenges, because features have different computational costs and different discriminative value. Computational cost is an application characteristic. The discriminative value depends on the feature itself. So you can do that for each of the features, but since this detection step has a cost, you don't want to do that for each feature individually. So you may want to cluster feature in steps and have a small amount of steps that you want to do in this iterative process. This is an example of applying just that. The application was seizure detection from ECG. This is a very challenging problem. We know that brain seizures affect the heart in really peculiar ways, but the medical knowledge is not set on exactly how this process works. What we can do is to take features which have been proposed by the state of the art, cluster them into many stages, and just use that for our incremental classification. We did that in collaboration with the University Hospital of Lausanne, which agreed to monitor for us epileptic patients during 40 hours of recording. So what we achieved are various behaviors depending on how much we decide to trust our results before saying, okay, this is the accepted result, and also how many steps we have in our model. In this case, we're talking about using 3 models and having a confidence threshold of 20%. So if our confidence is more than 20%, that we accept that as a result, otherwise we just iterate one more time using more features. And for that particular scenario, we obtain both pretty decent runtime saving and very little impact on the quality of our detection. In the previous result, what we did was to recompute everything every time we transition from one feature set to another. This is actually very wasteful because it means that we also recompute values which we already computed before, because every time we enlarge the feature set, this is a superset of what we did before. So this is the refinement of the previous framework. It's called ACE, Automated Optimization Towards Classification on the Edge. And what it does, it takes MATLAB code, maybe written by a biologist, written by someone which is not an expert in hardware software optimization, and it partitions it into multiple stages of this incremental process, and then translates that into C code, which can then be run onto an embedded device. First step, converts the monolithic classifier into an incremental one. It does that by looking at the application call graph. So function 1 calls function 2, and function 2 calls function 2.1 and function 2.2. And it looks at callers-callees relationship, but also at data dependencies in between functions. If this function computes something, and this output is used by another function, then it should be in the same subtree of the call graph, which computes a definite feature. Then what it does is that it buffers the data which is reused across incremental steps of the classification, so that every time we complexify our feature set, whatever was computed before is not recomputed anymore. Finally, it converts the high-level MATLAB code into embedded C and C++. This is something which we kind of got for free from a utility in MATLAB, which is called SzCoder, which translates MATLAB code into C code. We looked at 2 applications into this case. One is the same as before, seizure detection from ECG, and also some features from blood oxygenation. It's another type of biosignal. The second application is emotional state from ECG, respiration, skin temperature, etc. Emotional state is how much a person is actually stressed or aroused. In order to see how well our methodology works, we use all data is normalized to a monolithic model in which we just use all the features, and we compare that with a situation in which we had no buffering, which was our previous work. So in all cases it works well, which is something which we could not claim in our previous embodiment of the framework. If we don't do buffering, we may have cases in which we are actually doing more computation than just using all the features at once, because we have to do the detection again and again. If instead we do something smarter and we buffer the intermediate data, we always have a saving in terms of computation time, and we can have very decent speedups with very negligible degradations in terms of F1 score, so detection of either seizures or the emotional state for the 2 different applications. there is a dual to what I have just covered for a features-based flow into a deep neural network-based flow. So in the previous slide, we were talking about using incremental classification and using more and more features as we are not sure about the meaning of the data which we are analyzing. If we have a deep neural network model, we can do something similar by using more and more layers of a deep neural network as we are not sure about the meaning of the data. Instead, if the meaning of the data is obvious, we can just have an early exit, just plug in a fully connected layer on the side and have our outcomes as a result of this early exit. So this is something which I haven't contributed in research, but my good friend and colleague Marco Levorato at the University of Irvine has based his career work on this type of designs, and you're more than happy to look at his papers on this subject. Another take on that is that if we have an early exit, there is no reason why the later stages, which are only used seldomly, should also be part of computation happening on the edge device. So you may have something which is called split computing, in which the early stages are always at the edge, and if we are happy about our early exit, the computation just ends there. Instead, if we are not happy, then we can send the activations at this layer to a more capable device, for example, to the cloud, where a much more complicated and deep neural network can execute in order to have a more precise interpretation of the data. And this is the second transition which I wanted to do today, from a features-based flow to an ML or AI flow. In the features-based flow, we have signals which are conditioned, fused, and then we have some application-specific feature extraction, and then, and again, application-specific classification. In the ML case, we may do some lightweight signal conditioning, but this is by and large optional, and we just then take the samples and feed them into a neural network and let the backpropagation and the triggering process do the magic and interpret the data for us. Unsurprisingly, we have characteristics which are the dual with respect to what we had before. So ML-based flows tend to generate very general solutions. So if you want to adapt your network to a different application, just feed in the data and the labels, train your network, and use it for that. On the other side of the coin, we have a poor control of application size and complexity, so it becomes very challenging to embed this type of flows into edge devices with kilobytes of memory and few megahertz of clock frequencies. And embedding expert knowledge is very much a challenge. If you train a network and then a medical expert comes to you and say, look, I know that this particular feature of the signal is important, just cram that into your network, then it's not super obvious how to do that. Nevertheless, there are many applications in the medical domain which uses deep neural networks. I will present a few of them to highlight what are opportunities and challenges which Edge AI can leverage for the particular application, which is seizure detection. The literature is actually very vast with respect to different applications, but I hope, I've seen that, but I hope that by focusing on a particular application, we can just look at possible strategies. Please.
So out of the two flows, feature-based flow and ML AI flow, according to you, which one do you prefer, given that people are moving towards explainable AI and the second flow is not explainable at all?
So the question, yeah, I will repeat the question. So the question is, okay, there are two flows, which is one is better, and how to deal with explainability. So I will give an example of how we can sort of deal with explainability in the very last slides of today. So you have to be a little bit patient for that. As for which one is better, it really depends on what you're doing. If you're looking at maximizing your energy efficiency above everything, then maybe having a features-based flow in which you pinpoint what you're interested into may give you better results in terms of running in ultra-low power devices. If you can afford a little bit of generalization, then ML can help you because it can discover things which are even outside your particular expert knowledge. Having said that, in the last few years, intelligence at the edge has become synonymous with machine learning. I think this is a little bit partial. I think there is still space for embedding expert knowledge, extracting the proper features. Otherwise, you may have the first layers of a deep neural network, basically rediscovering FFT or something like this, just in a much more complicated way, computationally complicated way. Other questions? Okay. By and large, feel free to interrupt me anytime. I have plenty of slides, but there is no reason why I should go through all of them in case we have an interesting conversation on one particular topic. Okay, let me rewind a little bit. So where was I? Seizure detection using deep neural networks. Okay, so we would like to do this type of application. This is challenging, and especially challenging at the edge, because when we are having wearable devices, first, we have a lot more noise than in a medical scenario, in which we are much more controlled. There's a medical doctor assuring that everything goes fine, etc. Instead, if we have a wearable device and the person is just going around and living his life, there will be more noise. And secondly, because more often than not, we will have fewer signals. So this is what EEG acquisition looks like in a medical scenario, and we cannot really ask people to wear this 24 hours a day. And this is a prototype from our laboratory. It's called Epiphone, and it aims at being as unobtrusive as possible so that people can just live with it and it can be barely noticed while acquiring few EEG signals from selected position on the skulls. Secondly, discriminating seizures can be not super easy. So this is non-seizure EEG. It's kind of a rhythmic motion, and you can have that, for example, where people are brushing their teeth. They produce signals which are rhythmic in nature, and they kind of look like seizures, but are not. Or you can have motion artifacts which can just corrupt your signal and look like seizures. How to automatically detect seizures? Absolutely.
I'm no expert in seizure, but with ECG, as soon as you
So the question is how to detect seizures when people are doing daily life activities, like running around. I'm repeating the question for the video. So it is a challenge, and it is a challenge which doesn't have a silver bullet at this point. These are 3 examples of deep neural networks which aim at doing that. And they are successful or not depending on their complexity, but also depending on the training data that you use. Training data is key, and there is actually a paucity of databases which are connected from wearable devices as opposed to medical scenarios. This is also a challenge. So the short answer is there is no solution yet, but there are approximations to that. If you want to use a deep neural network to detect seizures, you may go slow, you may go small and use one-dimensional convolutional networks. You may go medium and look at two-dimensional representations of the signals, and this is a way to do that in which just every source of signal is juxtaposed to each other in a window which becomes a patch. Here is time, and here are the different contacts, and this is the input to my two-dimensional neural network. Or you can go full transformer, and transformers have been adapted to images. These are called vision transformers. Tokens are just patches of images, and since we can represent signals as two-dimensional patches, this can also be fed to a transformer model, which then does classification. In this particular case, this is one contact, and then doing the short-term fast Fourier transform of that. So here is time, and here are the different frequencies. This gives me a two-dimensional patch. I can feed that into the transformer, and each head of the transformer will process this patch in different ways. Of course, I can classify that in order to look at different signals at the same time. So how to train those models? This goes back to one of my first slides in which I was talking about the database and standardization. And one opportunity is to use few-shot learning. The idea is that we can use a large database to train a model, and then only few shots of a smaller database to fine-tune that for a particular scenario. This is particularly interesting if we have a large database of medical signals acquired with EEG caps and only small excerpts of signals acquired with a wearable device. Does it work? Apparently so. So in this case, we're using 2 different databases. We're training a model with one database and use just few shots of the second to fine-tune that. Few shots meaning that in this particular case, we're using 3 patients from the second database and the grand total of 16 minutes for each, for the 3 patients combined. So around 5 minutes for each patient, and we are reaching performances which are comparable to the ones which can be achieved by just training on the target database. Another scenario in which we can use few-shot learning is if we want to train models for different electrode positions. So if we have to choose some electrodes, because we cannot afford to have 20 of them, then the number of possible combinations explodes exponentially. In theory, we would have to train a model for each of the possible combinations, but this is very expensive. So what we can do instead is to train a baseline model in which we take examples for random selection of different combinations and then just use few shots for each particular combination. These are the results that my collaborator Alireza Amirshai obtained in the two cases of having a baseline model which is being trained for every possible combination from scratch, or having a generic model trained with random combinations, which is then fine-tuned with few shots for every particular combination. Results are very, very similar, but the training in this case took an humongous number of hours, while in this case, in 5 hours, we were done, and we had the map of all possible combinations of electrode with the model specialized for that. Further opportunity, personalization. So we have edge devices. Edge devices are given to people, and they're used to acquire data. Every edge device is different. We would like to personalize the model as it acquires data to become better and better. Now, this would be nice, but it has to confront with the fact that an edge device also has limited memory. So we don't have to use all the data which we are acquiring, but we have to be selective. How does that methodology works? So we again inspected the scenario seizure detection, and we started with a general model which was trained of a cohort of patients, and then we just used that to interpret data from a different patient. After a while, we used the acquired data to fine-tune the model for a small number of epochs. After another while, what we did was to transfer the data of past windows into a kind of long-term memory. And this long-term memory buffer, which we call the history buffer, contained all the seizure data and random windows of non-seizure data. Why we did that? Because seizure events are rare, likely so from a medical perspective, so we can afford to store all of them, even from the distant past, but we also would like to still recall what non-seizure data look like, even from the past. Then all the data which was acquired in the last window and this long-term memory buffer were used together to fine-tune the model. Now, this is the data set which we used. We went for the middle ground in terms of what convolutional neural network we want to achieve, and we had a number of baselines. So the kind of naive baseline was the one in which we had no personalization at all. Fine-tuning only used the last window for fine-tuning, but no long-term memory buffer. Only seizure is using a buffer which only stores seizure data, but no random windows of non-seizure data. And the history is a condition in which we just forget about having constraints on the amount of data which we can store, and we just use everything. So the challenge we had is that we wanted to measure how effective fine-tuning was while being independent for the particular network. So to do that, we started with standard figures of memory, like the F1 score and the false alarm rate, but from there we defined compound metric, which are called the remembering score and the future score. Remembering is how well we remember the past, so to measure if our methodology caused catastrophic forgetting, so that is no more able to remember what was going on. Future score is how fine-tuning helps into interpreting new data which has not been seen yet. These are the results for remembering, and we can see that we can remember pretty well, close to the results which we had while using all the past data into an unconstrained buffer. And also that this remembering helped us into predicting the future. So what we have here is that our results had the same F1 score with respect to the history scenario in which we have an unrealistic buffer which contains all the data, and also a little bit better false alarm rate. This is not statistically significant, so I won't comment further on that, but we can see that if we record only the seizures which we had in past events, our false alarm rate skyrockets because our models tend to forget what a non-seizure window looks like and tends to over-represent seizures. By having a little bit of seizures and a little bit of non-seizures from the distant past, we can counter that. Now, further opportunity is knowledge distillation, and I know that in the keynote speech which we had yesterday, we spoken a little bit about knowledge distillation, which means using a large model to train a smaller model. The way we use that in an edge scenario is a little bit different with respect to the one addressed in the keynote, because we wanted to train a model which only used ECG data, which is very easy to acquire. By using a bigger model, we use both ECG and EEG data. So during training, we have both EEG and ECG. During inference, we only have ECG. How we can do that? Well, we may use an ensemble layer which just averages the values which you have before the last fully connected layer, and then our dense layer which you have at the end is just ported to the student model, so that we can counter the fact that here we have a bigger model with more input data with respect to that. It works. Yes, it does, and it works way better than the scenario in which we don't have knowledge distillation, so we don't use EEG during training. We end up having an ECG-only model used during inference, which is way better with respect to the one which was trained using ECG alone. So, now yes?
So the teacher has just 3 models, and the students has 1 model. Then what do you exchange between them? Just the last layer, or what is this?
Yes, we exchange just so we have identical networks here, which are being trained, and here we do an assembling layer in which we are just averaging the values which we have before the last fully connected layer. And this can be directly ported to the student network.
One-to-one, imported one-to-one?
Yes. So the question is, can it be ported one-to-one? And the answer is yes. This is exactly how it works. This one does not. That's the whole trick.
Okay, you separate. Because we use another method.
So I am in a note right now because I have 5 more slides, but we are at the 75th minutes. So is it okay if we go 5 minutes over time, or do you want me to stop here? Okay, I take that as the majority says, but we want to stay here 5 more minutes. And let's talk about federated learning, which is another opportunity which is very much present in an edge scenario. Why? Because we are giving devices to people, and people are acquiring data. Everyone is acquiring different data. So can this knowledge be harnessed in order to better train the model for everybody? And this is the principle of federated learning, which is pretty cool, but it has to counter the fact that it requires very fine-grained synchronization between model updates. If we don't synchronize model updates very often, what happens is that every model kind of diverges, and then when we try to bring them together again, we don't improve our results. If you see, if we, every 30 iteration, we do the federated federation, then our results get better and better. But if we do that every 10,000 iterations, then our results actually get worse, which is bad. It means that we could do better without federating at all. So what my colleague in the embedded system laboratory did was to look at ways to make kind of a selected federated learning methodology. So data is acquired, updates are computed, then these updates are averaged in the cloud. After that, the updated global model is sent back to the device, and it is tested. Each device decides if it's better off with the federated global model or with its own or if its own updated model, and just chooses in between the two. It's kind of a simple tweak, but it works surprisingly well. And here you see the difference between the personalized federated learning, in which we selectively employ either the global fine-tuned model or the local fine-tuned model with respect to the standard federated learning. And yeah, app is better, so personalized federated learning is better. Last thing is about explainability, and here I'm going back to the question of the lady in the second row. So how we can cram expert knowledge into a machine learning model? The short question to that is that nobody is able to do that in a general way, and the fact that there are 800 references to this survey on explainable supervised machine learning is kind of a hint that many, many people have tried. Nonetheless, for some specialized cases, this can be done. And what my colleague Jonathan Dan was trying to do here was to estimate RR interval from blood pulse oxygenation. So this is a signal which can be acquired from a finger clip, very inexpensive, and measure the amount of blood which arrives at your fingertip, which is, of course, related to your heart pumping, but unfortunately is also related to movements. And separating these two sources, so the sources which we are interested into and the noise source, is very challenging. What he did was to train this source separation network independently using clean signals and signals corrupted by noise, and then comparing them. And he used that then in a flow in which a neural network was used to actually compute the RR based on blood oxygenation, and his source separation network was used completely independently to get rid of the noise and to estimate the impact of movements. You can see here the results. So this is our actual RR interval. This is the fast Fourier transform of the signal. And these are some noise corruption due to movement. If we don't use source separation, our detection picks up the noise pretty often, while instead, if we do use source separation, which is again a trained network, then the impact of noise is much less. Side note, the particular neural network which we used to do the detection is called QPPG, is from Alessio Burrello, which is actually giving his talk now in a different room. If you want more details about that, you can contact me. That's all for today. Sorry for being late. So today we look at what to compute, and we look at different ways to do data acquisition given the characteristics of the data which we are acquiring, and also to do data interpretation in a features-based scenario, in a machine learning-based scenario, looking at opportunities and challenges at the edge. Tomorrow, please come back again, because we will start to talk about architectures and how similar considerations can be applied when designing a computing machine. So thank you very much again for being here. See you tomorrow.